A healthy mammalian body is a remarkably efficient engine. Nutrients go in, metabolic processes extract energy, and the system runs in perfect balance. We call this state homeostasis. When you see a bag of premium commercial pet food formulated for daily maintenance, this is the exact baseline it is engineered to sustain. But that baseline relies on a major assumption. It assumes you are feeding a healthy, average animal operating under zero physiological stress, with perfectly functioning organs. In a clinical setting, that assumption rarely holds up. Patients undergo acute physiological stressors, like gestation, rapid skeletal growth, surgical recovery, and organ decline due to aging. When acute states trigger, metabolic demand spikes instantly. Chemical inputs from standard diets are quickly outpaced by new requirements. That deficit forces the body to react, clinically manifesting as anemia, malabsorption, or abnormal behaviors like coprophagy to reclaim lost minerals. When physiological demand outstrips the dietary baseline, relying on a standard bowl of food is biologically insufficient. The patient requires targeted chemical bridging to survive the deficit. Veterinary nutritional intervention is an application of precise biochemical engineering aimed at correcting specific metabolic failures. Exogenous interventions split into two distinct categories. You either provide the structural building blocks a body needs to create cells, or you introduce functional agents to do the work failing organs cannot. The first class is systemic bridging. This involves broad-spectrum vitamins and minerals acting as coenzymes to support high-demand cellular construction. The second class is targeted enzyme replacement. These are mechanical agents deployed directly into the gut to physically dismantle food. The third class is targeted electrolyte correction, which introduces isolated ions to counteract specific organ filtration failures. Effective clinical treatment means matching the exact biochemical intervention to the specific physiological failure. Let's look inside a stressed animal, specifically isolating the circulatory and skeletal systems. Consider a patient dealing with post-surgical recovery or a heavy parasite load. The body's immediate biological response to blood loss is erythropoiesis, the rapid, continuous formation of new red blood cells. To execute this process, the body requires iron, vitamin B12, and folic acid as absolute minimum chemical inputs. Without them, cell production stalls. B12 and folic acid handle DNA synthesis for each new cell. Meanwhile, iron sets the hemoglobin core, enabling it to transport oxygen. Now shift the focus to a different metabolic stressor, a pregnant female or a rapidly growing large breed puppy. These states trigger massive osteogenesis. Creating new bone rapidly drains the body's circulating reserves of calcium and phosphorus. You can increase the amount of calcium and phosphorus in the diet, but those raw minerals are useless without a biological mechanism to absorb them. Vitamin D3 facilitates the active transport of these minerals across the intestinal wall, regulating the specific channels that allow calcium to enter the bloodstream. At the same time, B-complex vitamins must be present to support the neuromuscular signaling network wrapping around this rapidly expanding skeletal structure. Broad-spectrum supplements like Nutri-Veg solve systemic bridging. They deliver the exact raw materials the body is desperately trying to synthesize, maintaining construction when dietary intake falls short. While systemic building blocks address cellular construction, we face a completely different problem when mechanical failures occur locally in the gastrointestinal tract. A prime example of this is exocrine pancreatic insufficiency, or EPI. Patients with EPI present a paradox. They consume more than enough food, yet they are actively starving to death. The digestive engine has stalled. Without a functioning pancreas, macronutrients simply cannot be cleaved for absorption. They pass entirely through the gut intact. This information sheet details the clinical solution, pancreazyme. This is an enzymatic concentrate derived from whole raw porcine pancreas. This exogenous intervention dumps standardized, active enzymes into the gut lumen, where complex food molecules remain stubbornly intact. Amylase gets to work, targeting and severing complex carbohydrates. Next, protease steps in, dismantling tough protein bonds into absorbable amino acids. Finally, lipase enzymes target the dense, stubborn lipid molecules, aggressively dismantling their chemical bonds to produce much smaller, highly absorbable fat fragments. Enzyme replacement manually executes the mechanical digestion that the host pancreas is no longer capable of performing. If we move from the mechanical digestion of the gut to the precise ionic filtration of the kidneys, the intervention strategy shifts again. Looking at this specification document again, the focus turns to Tumol-K, a highly specific potassium gluconate intervention designed to treat potassium deficiency. The primary clinical stressor here is chronic kidney disease, a frequent organ failure particularly in aging felines. This progressive damage often leads to hypokalemia, which is the dangerous systemic wasting of potassium. Healthy kidneys filter and reabsorb potassium ions into the bloodstream. Failing kidneys lose this retention mechanism, allowing crucial potassium ions to leak entirely out. Introducing potassium gluconate floods the system with a massive surge of new ions, overwhelming the leak and reversing the deficit. Because the leak remains constant, this intervention requires strict twice-daily dosing to continuously maintain the electrical action potentials required by the heart and kidneys to keep beating and filtering. When an organ's fundamental retention mechanisms fail, targeted electrolyte correction is required to maintain the ionic balance necessary for basic cellular function. Zooming out from the cellular level, the biological reality of the entire organism becomes clear. We've examined 3 distinct vectors of clinical veterinary intervention: bridging the gaps in cell construction with broad-spectrum multivitamins, replacing lost mechanical digestion with exogenous enzymes, and stabilizing renal filtration with isolated electrolytes. Clinical veterinary nutrition is an exercise in applied biochemistry, deploying precise chemical solutions to solve specific biological failures. By understanding these mechanisms, veterinary professionals can look past the illusion of the complete maintenance diet and successfully treat the animal's actual metabolic reality.